Thank you for coming to the 36th annual Sweeny lecture. And I would like to introduce the master of the ceremony for this evening, our chair, Professor Pam Mills.
Thank you, Andre. So I'm happy to welcome all of you, particularly the students and the alums of Lehman and the chemistry department. So before we get started, let me find out just by saying yay. Who are the students here from Lehman? Who are the alums? Oh, alums, come on, you can be louder than that, right? Okay, are there any alums of Professor Sweeny? I know there's one. There might be more, there's two. Okay. This is the 36th annual Sweeny lecture, a lecture series that was created to honor Professor Sweeny. Professor Sweeny began his career in CUNY in 1930 at Hunter College. In the late 30s, Hunter College expanded into the Bronx and was built. So this campus was Hunter College. In 1968, this campus became Lehman College. Professor Sweeny chose to continue his career here at Lehman until his retirement in 1974. So Professor Sweeny loved chemistry. He loved the science of chemistry, but I think most importantly, he enjoyed sharing his love with his students. He really represents and embodies the quintessential professor. He inspired and empowered his students to be more than even they thought they could be. So 36 years ago, his students asked then Professor Leonard Leaf to establish a lecture series and in his name to honor him in perpetuity. So this is the 36th year of this. We missed 2 years, sorry. So,
I just find out.
Okay, but this year, one of his students, Dr. Jeff Gilbert, has asked to speak about Professor Sweeny. So I'm going to introduce him. Dr. Gilbert graduated from Lehman in 1972 and then went on to graduate from Albert Einstein College of Medicine in 1975. Dr. Gilbert has had a truly illustrious career. He's been serving really the people and the families of the Bronx ever since. He was appointed an assistant clinical professor at Einstein of medicine and of OBGYN. In 1992, he established the STD Center at the Mount Vernon Hospital and then moved the clinic back to the Bronx to Montefiore in 1996. And he was with this clinic, I believe, until 2013 when he retired. That's very interesting. But more interesting is what I found was more interesting is he was nominated to be a Best Doctor of America list, I think 7 years in a row. But even more interesting than that, he's the author of a children's book called Milton's Moment. And then even more interesting than that, he's a driftwood artist. So here's a picture I found on his website called Rhino. And these are driftwood that has been harvested, I believe, from the Hudson River. So he's a local artist, doctor, and graduate of Lumley. So Dr. Gilbert.
Thanks. Always a pleasure for me to come back to Lehman, and I have felt through these 36 years it's important for people who didn't know Professor Sweeny to learn just a little bit more about him. It's wonderful that this lecture keeps on going, but I just wanted to share some of his pearls of wisdom and a little bit about him. As you heard, he was here for many years. First lecture was in 79. He retired in 74. I graduated here in 72. And I had him as a professor in 71. And I heard a lot about him. I was a little afraid to be in his class, but it turned out to be one of the highlights of my life, being in class with Professor Sweeny. He had a wonderful tradition. On Friday, we had organic chem lab. And he always provided peanut butter and Triscuits for us in his office, so it encouraged the students to come into his office and sit down while Bunsen burners were heating liquids and talk with him. And he always wanted to know about you. He wanted to know what was in your mind, what ideas you had, how you saw things. And that was very unique, that somebody of such stature cared what his junior and senior students were thinking about. He had a research project here, a cancer research project. He had students synthesizing chemotherapeutic agents, and the last year we tested it on mice. Leukemia was L1210 that we tested his compounds on. This is where Professor Sweeny lived. He lived in Pleasantville for decades and decades and decades, and that porch was very special to me and other students because we used to go to his house and watch the 4th of July parade pass by. His wife, Bailey, would have some snacks and drinks, and then we'd watch the parade. And one year, he took us, he took me, and he took Sydney, who's sitting in the first row, Sydney Sudberg, and Ronnie Goldfarb, one of his other students. He took us up to the Beaverkill River in Roscoe, New York, to go trout fishing. And in all my wisdom, I really didn't know that the water was that cold. I wandered in, and my legs cramped, I couldn't get out. So he put on his waders and walked in the middle of the river. I got on his back, and he carried me back to the shore. Sydney and Ronnie slept in a tent on the shores of the river. Professor Sweeny and I slept in a motel. It was pouring that night, if you remember. You braved it, we didn't. In '74, Professor Sweeny was the Grand Marshal at graduation here. And one of my most proudest moments was in 1975 when I graduated from medical school. He was sitting with my 2 grandmothers and he at my graduation. It meant quite a bit to me that he was there. This is the Sweeny boys, one of the few pictures, and girls, and to his credit, many of the students here went on to graduate degrees, MD degrees, etc. David Villabrera over here. Well, let's see if I can do this. David Villabrera here became an MD. Next to him, John Birigo became an MD. This guy became an MD. I don't remember his name. That's Brenda Moffitt. She was a wonderful bio professor for years here. And here's Sydney. Sydney looks exactly, pay attention to who he is, because he looks exactly the same today as this is 43 years ago, and you look exactly the same. Barbara Edelstein is a world-famous radiologist in New York City, women's mammograms, etc., very well known. So he shaped our lives. He shaped our lives by teaching us organic, but he shaped our lives by giving of himself. He shared himself with us. In his later years, I used to go visit him in Pleasantville. I moved 2 miles away, and I used to go drive down and visit with him. And as he got older, he started worrying almost obsessively about what he was going to do with the 8,000 chemistry magazines that he had stored in his basement. And I went down to his basement, and his basement was ceiling to floor, wall-to-wall magazines. And he tried to give them away, and nobody would take them. And it was really upsetting him. So as a surprise, I hired a demolition company to come one day when he was out. I did this with his wife. She was thrilled that these magazines were going to leave. And we loaded them up, or they did, on their truck. And they told me half price if we don't have to find a place to put them. So I said, you'll put them on my property. So this was the walkway leading from my house, and I had them put all of those 8,000 magazines on this slope, and then I covered it with some leaves. And about 8 years ago, I knocked that house down, and the guy who was doing the landscaping said, I'll redo the whole property. I said, not all of it. I said, right over there, I don't want you to touch this area here, because this is where knowledge from my professor, who I loved, is buried, and I don't want you to touch it. And 3 years ago, I was in the library in town, and I happened to see Professor Sweeny's grandson, Peter, and his son, Bradley, in the library. And I told them, can you come over to my house? I want to show you something. So I took them here, And we stood right here. And I proceeded to tell his son and his grandson about the magazines and his legacy. And I had his magazines and some of his papers buried here and covered, and the grass is growing nice. And I said to them, I just want to let you know, I call this Sweeny Hill. And anybody who comes here has to hear the story of what Arthur Sweeny meant to me and Sweeny Hill. He had a few pearls. I'll end with some of his pearls. His pearls got me through life. One of his pearls was, he told me, when you go into medicine, learn everything you can about one thing, but learn like every single thing there is to know about one thing. And when you do that, everybody will come to you for that knowledge. And I followed his advice, and he was 100% correct. The fourth pearl he had, which has also gotten me through numerous lectures, he told me, if the key to a successful attendee-ship at a lecture is, never let anybody sit between you and the door. We loved him, we really did. He was like my grandfather, and I am so grateful that I had that opportunity to be in his class and to be in his life. And it's something all students should try to do. Find a mentor and get to know that mentor. And if they'll share that with you, you have no idea what it's going to mean 10, 20, 30 years later. Thanks.
Thank you, Dr. Gilbert. It's a wonderful legacy that we have here in the chemistry department at Lehman. So before we start our lecture, it's traditional to take a few moments to just highlight some of the accomplishments of the year from our department. Now, for most of you, you received a letter from me which went through the list of accomplishments, so I'm not going to repeat those. Instead, I'll tell you a few things that have happened even since then. Well, one that hasn't, but I think it's important, which is just to recognize that we have a new faculty member in our department this year. Professor Benjamin Burton-Pye joined the faculty this fall and will be starting a radiochemistry program here as soon as his lab is finished. Have you heard that story before? So I hope to report next year that the lab is done. Very recently, we also found out that Professors Burton-Pye, Lopez, and McGregor won seed grants to work at the Advanced Science Research Center that's on the campus of City College. So we've been building our relationship with ASRC, and it's really exciting to get this seed grant. We also found out just recently that Professor Lopez, who's a co-PI on a center grant called CREST from NSF, it's a multi-million-dollar grant, was just awarded to City College in Lehman. So we're really happy about what our faculty do, but we're really happy about what our students do. We're very proud of our students, and it's much more important to us in many ways. And so I want to just talk about 4 students who have won summer research fellowships. I think it's the largest number we've had. Let's start with the ASRC. CUNY has now a prestigious summer research program called CSERP. The students all go to ASRC, and it is a national competition. It is not just given to CUNY students. This year, we are pleased that one of our chemistry students, Joe Cruz, who's a junior working with Professor McGregor, was one of the awardees and will be spending his summer in Manhattan. In addition, George Mayo, also a junior, is working with Professor Malakarachi. He won the prestigious William H. Nichols Summer Fellowship Award. He'll be staying here in the Bronx and working here on campus. Gabriela Rodriguez, a student with Professor Gitiano, she will be sponsored also here on campus, but by Columbia University, she won an NERA med prep program to work on campus. And lastly, Martin Kovalev, also a student with Professor Gitiano, has won an award to go to the University of Puerto Rico in Rio Piedras on an REU NSF fellowship. And then lastly, we will hear more about our 5th student, but only after the lecture. So anyway, I want to congratulate all 4 students for the summer. Our speaker this year is Professor Richard R. Schrock. Professor Schrock is the Frederick G. Keyes Professor of Chemistry at MIT. In 2005, he, along with Yves Chauvin and Robert H. Grubbs, won the Nobel Prize in Chemistry for the development of the metathesis method in organic chemistry. Today, he will talk to us about his journey to the Nobel Prize and beyond in a talk entitled The Continuing Saga of Metal-Carbon Multiple Bonds. Professor Schrock. We need to shift this from here to here.
Thank you very much, Pamela. Thank you, Andre. Everyone who had a hand in getting me down here. It was a very educational day, and I enjoyed it very much. We had beautiful weather. The trees are blooming a little more than they are in Boston, I think, and it's nice to come back to this part of the world where my wife was born, in fact, Manhattan Hospital. But she lived in Farmingdale, and then she moved up to Lexington at a young age, 10 maybe, and ultimately I met her there in graduate school. And as you'll see, although I'm not giving what is called the really light talk, this is going to have a little more chemistry in it than the full public talk. So some of you are going to have to hang in there, but I hope you find it interesting. Now, if I can figure out what to do here, here we go. Yeah, you know, I think it could we dim the lights maybe a little bit? Is it possible? Because the screen will be a lot easier to see if we dim the lights. We can't see the screen. So I was born in Indiana, and when I was 14, I moved to the West Coast with my parents. My father decided to go into business of building houses with his brother. And so I went to half year of junior high school, and then went to high school for 4 years in Mission Bay High School in Pacific Beach, California, which is near San Diego. When it came time to go to undergraduate school, I decided to go to Riverside, which is not too far away, straight north, about 90 miles. And there are various reasons for that. I won't go into it, but I knew they had a good chemistry department, and they had somebody there named Jerry Bell, who was from Harvard University, and ultimately I took a class from him, and ultimately I ended up applying to Harvard University for graduate school and going there for graduate school in 1967. I guess we still don't have the lights dimmed, but we can't see this very well, but this is a picture from that time. This is the Osborne group. So this fellow is John Osborne. That's me with my hand on Dave Rice. And here's John Shapley and Jay Labinger. And let's see, I don't know this fellow. Steve Wilson, a couple of other people. But he changed my life. And this is the order in which we joined the group. I was really his first student. So John Osborne was a student of Jeffrey Wilkinson, who received the Nobel Prize in 1973, and this was his first appointment at Harvard University in 1967. I went to study in Europe, in England, in 1971 at Cambridge University. In 1971, there were no jobs, and I don't mean there were a few jobs, I mean there were no jobs. I didn't know that when I was getting my degree, but I was fortunate enough, and like many fortunate incidents in one's life, I was fortunate enough to get an NSF fellowship. That was the last year that the National Science Foundation gave a postdoctoral fellowship. So I went to study in England. My wife and I got married. We went to England, and for the first 2 weeks we were both deathly ill from something we had picked up along the way. But otherwise, the year went swimmingly. And I didn't learn much chemistry, but I had a wonderful time. We had a wonderful time, except that there were not very many more jobs in 1972. And I met somebody from Central Research and Development Department at DuPont named Earl Mutertes, and he made me an offer later when I visited to come to DuPont, and I had some offers to go elsewhere in academics where I really wanted to be, but this was the best place for me at the time. So they had a central research department where you could do research, you could invent something, which is what they paid us for, and maybe ultimately that would become commercially viable and they would make some money off of it. But they had enough money to invest in that idea. Sadly, today, that's gone completely. As you might have heard, the merger of Dow and DuPont resulted in more or less everything at DuPont being, in terms of research, being eliminated. So my forming ground is gone. When I went to DuPont, of course, DuPont is famous for polymers. And when I went to DuPont, they said, look, you can do anything you want as long as you make a polymer. And I said, okay, I'll make a polymer, but I want to do something besides everything else that you've done. So I want to choose some chemistry that nobody else has done, and that's been my rule ever since. You've got to look somewhere else in order to make a discovery. Otherwise, somebody else probably has already done most of the work. So when I went to DuPont, first of all, I did most of my graduate work on rhodium. You will all recognize this as a periodic table. We're now out to number 118 as a certified element, which is now the highest number here at the end of what we call the fourth row of the transition metals. These are all radioactive, of course, so it's really these three rows in the middle of these transition metals that were of interest to me for what they can do. Catalytic reactions, which I learned with John Osborne. In that case, it was just hydrogenation of olefins, alkenes, carbon-carbon double bonds. Those involved rhodium complexes. When I went to DuPont, I decided to wander all the way over here and settled on tantalum. Now, tantalum, that's where the word tantalizing comes from, by the way, is right below niobium, right below vanadium. Niobe was the daughter of Tantalus, so that's where those two names come from, and this one is derived from the goddess of some Swedish goddess, Vanadis, I think it is. Anyway, I decided to work on tantalum chemistry and to do organometallic chemistry because all of these catalytic reactions that I knew of, or at least most of them, involved metal-carbon bonds, metal-carbon single bonds, which are called alkyl complexes. So I thought, well, I'll make some alkyl complexes maybe. And I was in the process of doing that. I discovered a paper that I'll show you in a minute, but here's this fellow, Jeffrey Wilkinson, who was a consultant at DuPont. So that was back in the days when they have experts come in and talk to these super postdocs that they hired as researchers at DuPont. And he told us about a compound called hexamethyl tungsten. Now, I remember giving this talk, I think it was in Winchester, where I live, and one of the people who knew no chemistry came to me and said, what was that me stuff in the talk? I said, well, that stands for something. It stands for methyl CH3. But I thought that was pretty funny. Me. That's what it says. This was made by Jeffrey Wilkinson. So this is a CH3 6 times around tungsten. The oxidation state of tungsten, we would say, is in the highest possible oxidation state, +6. It's in group 6. Highest possible oxidation state is +6. At the time, people thought that metal-carbon single bonds were unstable because people could not make compounds like this revolutionary compound. All they could do was to find the products of their homolytic decomposition, a breaking of that metal-carbon single bond, methyl radicals and other decomposition products. But they are quite strong, especially in the third row where tungsten is in that periodic table, and do not cleave readily homolytically. In his Nobel Prize lecture in December 11th, 1973, the ceremony is on December 10th, so I don't know why this talk was on December 11th, but that's what it said on the web. He noted that he had come to visit DuPont and that he talked about this compound, and then he said that hexamethylrhenium, it was made by him, and pentamethyl tantalum, he left out the T here, pentamethyl tantalum was made by me, private communication. So I made pentamethyl tantalum because I could subtract 1 from 6 and get 5. And that was my boost in this area. The other boost was given to me by a guy named Gordon Juvenal, who I never met, but I knew that he had made a compound having 3 methyl groups and 2 chlorides on it. That's tantalum 5 then, highest oxidation state. And I decided that I would simply replace those 2 chlorides with methyl groups and make pentamethyl tantalum. And like hexamethyl tungsten, only very much worse than that, this pentamethyl tantalum decomposed pretty violently sometimes in an intermolecular fashion. Now, what does that mean? It means 2 of these came together and one of them reacted with the other, and it set off a sort of chain reaction and made a lot of methane, about 3.5 equivalents of methane, and a lot of uncharacterizable brick dust, more or less. 3.7 it says there. Gordon Juvenal, I discovered, died in 2013, so I was sorry to hear that. I never got to meet the guy who, in fact, started my career in an important way. So what do you do as a scientist? Well, you can subtract 1 from 6, that's fine. And then you say, well, this one's unstable because of an intermolecular reaction. I'll just make these things around the metal bigger. Stop that. People were interested in this type of blocking, if you like, of decomposition because nobody knew what happened when you stopped these decompositions of especially groups that don't have any second carbons there with protons on those carbons. And that's true of this benzyl group. So I made tribenzyl dichloride and made pentabenzyl tantalum, which is stable at room temperature. It's unstable when you heat it up. And when it does decompose, it decomposes in what's called a unimolecular decomposition. So it's not bimolecular. Something happened within the metal to generate a product. And there was a possibility, I thought, that what had actually happened is that it made one equivalent of toluene and formed this tantalum carbon double bond, question mark, question mark, question mark. This couldn't be isolated because these groups are actually too small, as we'll see. What does not decompose is the analogous neopentyl. So what's neopentyl? It's simply a carbon with another carbon and 3 methyl groups on it. CME3, me again. There we are. And if you add, you attempt to make the pentaneopentyl tantalum, fortunately it's unstable and it decomposes intramolecularly. Essentially, one of these neopentyl groups grabs a proton from the alpha carbon of a neighbor and creates this double bond and neopentane, which is a gas at room temperature, and forms this tantalum carbon double bond. Not only that, but this compound is very stable. Not towards water and oxygen. You have to do all these reactions under an inner atmosphere, but towards thermal decomposition. So bimolecular decomposition is completely blocked, and there's no intramolecular decomposition. At this point, only these 5 coordinate species, 1, 2, 3, 4, 5, with big groups on them, will decompose to give that double bond. So this is the first, what's called an alkylidine complex, or also, as you'll see, called carbene complex. CHR is actually what's called a carbene if it's not attached to something. It's very reactive and is only tame when it's attached to a metal. This compound actually can be distilled in a good vacuum, and it's really quite remarkable even today that you can do that, and it's really one of a kind. Now, this is my lab notebook. We had to keep lab notebooks. So this is July, you can't read it probably, July 27, 1973, A, B, C, small scale, medium scale, large scale reaction. There's a lot of stuff written here that I'll tell you about. It was witnessed by a guy called Fred Tebbe, and some of you, and maybe one of you in the audience has heard of Fred Tebbe. He's got a name attached to a compound called Tebbe's reagent. He was my lab mate. I actually learned a lot from Fred, too. That's why I think I did what I did. This is what's called an NMR spectrum, nuclear magnetic resonance. It tells you what different kinds of protons are present in the molecule that you made, this new thing. And I knew that there was 1 to 9 to 27 to 6. It's not pentaneopentyl because that only has 2 types of protons. So it has to be something like this, I thought. So this would be 1 to 9 to 27 to 6. And this was not before. This was before pulsed NMRs. These are back, continuous wave with a pen that goes across the paper. Well, I decided that this was not the answer. It was actually this double bond that I mentioned. I said, could be. This is the actual picture of it. I still have this. I showed it to my class that I taught earlier this semester on organometallic chemistry, and said it could be this thing with a tantalum carbon double bond, never been seen before. And that turns out to be the case. And why is it not the dimer? And that's because when you do a molecular weight study in benzene, you find that it only has half the molecular weight that you would expect for a dimer. And there are other reasons, which I won't go into, but I went home and told my wife that, Nancy, I think I've done something, and I think I said important. I can't remember. Was it important? I said interesting. Okay. I think I've done something interesting. It's about as excited as scientists get, I guess. Fred Tibby signed this on December 10th, 1973, so a few months later. Everybody hated witnessing experiments, so they would put it off until the end of the year when you had to do it. The other thing that I discovered before I left DuPont in 1975 was the fact that you could take this compound and add some external base that would remove the proton on this new kind of ligand called an alkylidine and make a tantalum carbon triple bond. And there's a lithium plus then that goes along with that. This is just one way you can draw it. But it showed that the first proton on these neopentals comes off slowly, intramolecularly, and then you can pull off another one and make a triple bond. So you can make double and triple bonds bound or between carbon and tantalum of a type that had never been made before. There's another type of each that had been made by the guy who shared the Nobel Prize with Jeffrey Wilkinson in 1973 for sandwich complexes like ferrocene and chromocene, but both of them, or at least Wilkinson, was interested in other things, alkyls, and Fisher, in fact, in double and triple bonds. So he made compounds of chromium that contained this chromium carbon double bond in 1964, so 10 years before I made mine, and he called it a carbene complex of chromium 0. So no charge on that carbene. And then he made a metal carbon triple bond in 1973 when I was at DuPont. He called this a carbine complex, just R with C bound to the metal. And both of these descriptions are approximately correct, but the oxidation state of the metal was quite different than the highest oxidation state that I'm talking about in the case of the trineopentyl neopentylidine tantalum and trineopentyl neopentylidine anion tantalum, which is the tantalum 5, the highest possible. So we learned that you can make then electron deficient metal carbon double bonds and triple bonds. I'm just going to talk about double bonds today. And these are isoelectronic with oxo 2-. So that is a 2- ligand, and that's where the tantalum 5 oxidation comes from. And they're pretty stable, or can be quite stable. And you can take off more alpha protons to make triple bonds from double bonds, but it's that removal of an alpha proton from a carbon directly bound to the metal that gives that first double bond. That was the big discovery. Now, why was this interesting to anybody? Well, there was, at the time, around 1970 to 73, a lot of discussion about an interesting new reaction. So I talked about alkenes. These are alkenes, or olefins, O-L-E-F-I-N-S, carbon-carbon double bonds. There are a lot of carbon-carbon double bonds around. They're in nature, they're in cooking oil, they're in you. They're strong double bonds. Single bonds is what holds you largely together, and they're strong too. You can't pull them apart. And in fact, if you have some red and blue, this is a rather Democratic Republican fight here, olefins, they don't scramble. That is, let's say that CHR end doesn't get scrambled with the CHR prime red end. You can't make this species because these are strong. You can't just go around chopping these in half because the resulting pieces that you chop in half are very reactive and do all sorts of other things. But there was a reaction out there that everybody was trying to explain. And it was ultimately named the olefin metathesis reaction. So metathesis means metathesis. In England, they say metathesis. And so it means switching places. And there are other instances where you use metathesis or metathesis. You replace one thing with another. In this case, it has to do with replacing one end of the olefin with the end from another olefin, making a new olefin from olefins. This was patented or appeared in the patent literature or published early on, starting in 1955. And what happens in the presence of a metal, which happens to be molybdenum or tungsten or rhenium, you can carry out this sort of scrambling reaction where this is an unsymmetric olefin now. You can make an equilibrium that contains it and the two symmetric ones. Now, olefins have different forms. Cis forms, where these R groups, or here R and R prime, are on the same side of the double bond, or opposite sides. This one's called the cis or Z form, and this one's called the E, or trans form. So you end up, if you start out with one of these 6 possible forms, you make a mess. You make a mixture of them. So that doesn't sound very productive, and initially that wasn't very productive. You don't want to turn one nice compound into a mess of everything. But gradually people got to understand this process. A guy named Calderon really made reproducible catalysts from tungsten starting compounds like tungsten hexachloride. There's the guy Chauvin, who was the first to propose a mechanism for this reaction. So how do you take the ends of olefins and scramble them? Well, he said there must be a metal-carbon double bond. This was 1971, before I discovered this new compound. Metal-carbon double bond that reacts with carbon-carbon double bonds to make a ring. So these two R groups get next to one another, and then you take out the symmetric olefin and you make the next alkylidine, next possible alkylidine, and you do that twice and you can carry out this scrambling reaction. But nobody was able to apply this to organic chemistry because nobody knew what the compounds were. How do you make them? They weren't the Fischer-type compounds. They didn't work. So it must be a new compound. So that was back in 1971. 1974, I came along and I said, well, maybe the things I made are relevant to this reaction. Now, for those of you who are a little more chemically challenged, I'll show you in human form what the olefin metathesis reaction is like. So this is part of a video I never did get to work that a Hungarian friend of mine sent to me. This is, although it's still a little too bright here, but this lady in dark is the catalyst. And she is the only one who can switch partners. All the other people here who have double bonds, you're holding each other's hands, they can't switch with anybody else. Only she can switch. She has an original partner here in orange, and she goes and she grabs either the red or the blue partner. I think she's going to grab a red or blue partner. There. She grabbed the red partner, and look what they did. They made a ring, just like Chauvin said. And this is really a do-si-do. It's a square dance sort of thing. And then she takes this new partner and leaves her original partner with her, and then she goes off and finds a blue couple to make a ring. And then she takes the blue partner and so on and so on. She scrambles all the dancers here on the floor to give all possible combinations. And she does it by making rings. Now, what was I going to say? Oh, the reaction is not what you want, of course, right? You want somehow for her to say, okay, I want you to do this, I want you to do that, and forget all the other reactions. I will guide the way, I will guide you to find the right partner. That was the challenge chemically for me, ultimately, to figure out, and I'm still working on that. Now, equally curious was the acetylene metathesis reaction. So that was discovered first in a heterogeneous reaction in 1968, and then in a homogeneous reaction by Mortreux and Blanchard in 1972, when I was at DuPont. And it's a reaction in which triple bonds are in fact scrambled. And that's even more bizarre. You know, how does this happen? And these are fast reactions. Boom. So how does this happen? Well, it happens the same way as opposed by Tom Katz in 1975, that there is some compound having a triple bond in it, bound to a metal carbon triple bond, that reacts with a carbon-carbon triple bond and forms a ring. And then if you put the two R prime groups together, you can take off this new acetylene and make a new alkyladiene and go around again. This is called a metallocyclobutadiene intermediate, because they're really double bonds that have been created in this ring, and this is a planar intermediate. It's a little hard to show this using dancers, because dancers only have two arms, and so I didn't do that, didn't attempt to show that with a dance troupe. But it's actually triple bonds, and the mechanism is the same. Metal-carbon triple bonds react with carbon-carbon triple bonds selectively, and metal-carbon double bonds react with carbon-carbon double bonds selectively by those same rings. One a metallocyclobutane ring, one a metallocyclobutadiene ring. We found that we could, in fact, make these catalysts for acetylene metathesis by making compounds having these triple bonds in them, replacing the neopentyl groups with chlorides, and then replacing the chlorides with alkoxides, 3-T-butoxide groups in 1982. And these turned out to be for the first time, very active, obviously identifiable, what I call well-defined or well-characterized catalysts for this reaction. So you take a little bit of this, and you can, in fact, scramble the ends of ethyl propylacetylene or 3-heptine to give all possible products. There are only two possible products, because now you don't have isomers of carbon-carbon triple bonds like you do of double bonds. So that's a simplification of acetylene metathesis versus olefin metathesis, but olefins are much more common, so I started to focus on olefin metathesis. So what kind of tungsten compound? Tantalum didn't work, right? Tantalum wasn't one of these classic catalysts that you can just generate by dumping things together, a kind of natural product. And so it has to be tungsten or molybdenum, but what kind of compound is it? And I thought, I had a great idea, and I said, look, why don't you take a tungsten 6 oxo complex and a tantalum 5 alkylidene complex, and these two are both 2- species, and switch them in what's called you would call it a Wittig type reaction. For those of you who know some chemistry, there's something called a Wittig reaction, where you react phosphorus carbon double bonds with carbon oxygen double bonds. And that's the sort of thing I wanted to do. Fortunately, that didn't happen. So another lucky break, everything else happened. The oxo didn't go anywhere, it stayed on the metal. And these two ligands, which are called phosphines, went onto that metal, and two chlorides went onto that metal, and one chloride remained behind, and the T-butoxides went over there. So it was a dramatically complicated reaction, but the only product at the end was this one. And it turned out that this is now what we call a tungsten 6 species. There's a 2-, a 2-, tungsten 6 with two phosphines bound to the metal. And we could show that this compound, in the presence of a little bit of a Lewis acid, as it's called, to maybe remove the chloride a little bit or the phosphine a little bit, that this was actually a metathesis catalyst for olefins. So that was the first time that anybody had made anything that could be identified. Not only was it new high oxidation state, so-called D0 species, but it actually did the metathesis reaction. And you could see the new alkylidine that you made after it was all over, or alkylidines in some cases, more than one. We weren't successful in making other variations of this, in particular 4 coordinate species, what we call oxoalkylidine bisalkoxides, so-called 4 coordinate species. Again, there's this theme of 4 coordination, big bulky groups, no matter what they are, oxo, alkylidine, or alkoxide attached to the metal. But we were successful at using a bulkier 2- ligand, if you like, as an X group in place of O. So this is N with that group on it, 2-. And we found a way to make those. And we found alkoxides that were large and sterically demanding. So we made a whole bunch of compounds that looked like this. So we made them, and I won't go into detail, from the metal-carbon triple bonded species. So that's where a role that the metal-carbon triple bond, a very important one, played by attaching this aerial NH group and then moving the H from the N to the carbon. That generated this metal-carbon double bond and then a metal-nitrogen double bond. This one doesn't do anything in all these reactions. It's what's called a spectator, because it has to be carbon. If you want to do metathesis, we're talking about carbon, and so it has to be the carbon piece that does the job in these remarkable reactions. So we made a large number of variations. Here's a crystal structure of one of them. They're all very sterically demanding. This is called a first generation imido, that's the N part, alkylidine. There's the alkylidine. Bisalkoxide, T-butoxide in this case, in 1987. You'll see that one of the things I want to point out, and you'll see this later as we go along, that once you know what a catalyst is, you make it, you do a crystal structure, you say, oh, problem solved. We can just do anything we want. Well, not so simple, because this lady in black has to move the people around, so you got to move the olefin ends around exactly the right way to get a given desirable result, not just make a mess. So this T-butyl group on the alkylidine carbon here is actually this carbon is in that plane. That carbon, the tungsten, and the nitrogen form a plane, and the T-butyl group points one way. So this is kind of a cis metal-carbon double bond. So there might be a trans metal-carbon double bond with this pointed the other direction. In fact, that's true. That's a remarkable complication that turns out to be something you have to deal with. So we made these types of catalysts, not only for tungsten, but for molybdenum, and started to use them for all sorts of reactions involving taking carbon-to-carbon double bonds from some olefins and changing them into different kinds of carbon-carbon double bonds, and maybe a product that we don't care about, like ethylene, and take it away. Is catalytic. It's clean. Catalytic reactions are good, right? You don't make any really terrible other products except other olefins, which you can recover, like acetylene or like ethylene. And it's very fast, and it will do things, as you'll see, that cannot be done really, certainly as quickly or as efficiently any other way. This is called a second generation catalyst. Now, second generation just happened to be in collaboration with a guy named Amir Hoveda, the first variation that we tried starting in 1998 to apply to organic chemistry. So you want to do organic chemistry here. You want to take organic molecules and make new variations cleanly and quickly and catalytically using double bonds as reagents, which you can recover, and it's all a closed cycle. So this, instead of two alkoxides on the metal, here's the alkylidene, slightly different kind of one, having a phenyl group on the beta carbon, and here's the amido group. These two alkylidines have been replaced, or instead of two alkoxides have been replaced by what we call a chelating biphenol, which is chiral. So this is like a left hand and right hand. It is non-superimposable on its mirror image, this ligand. So that makes the metal itself chiral and enantiomerically pure. And the idea was that you should be able to do these carbon-carbon double bond reactions to make enantiomers, right-handed species, selectively only, or left-handed species, selectively only. Because you all are full of unsymmetric centers of that general type, chiral metal center, or chiral carbon centers. I'll show an example of that in the next slide or two. Generation 3, this is in, now we jump ahead all the way to 2007, still in collaboration with Amir Hoveda, and we are in our 18th year of collaboration, and I'll show you the most recent results toward the end of the talk that were published in Nature about a week ago. Now, let me point out some of the problems. One of the problem is that there's not one catalyst there. There are a whole bunch of catalysts. Anything that has a carbon that can be doubly bound to the metal, any piece of an olefin is an intermediate in this reaction, so all those compounds. But there are, as I said, two forms. This is kind of a cis form. It's called a syn form. It's usually the favored form, the one that's the lowest in energy, for reasons which I won't go into. And then there is a trans form. You might call this a trans form. That's called the antiform. Those are different compounds. I mean, they look exactly the same, but they are different, and they have different reactivities. And they have different consequences when they react with a double bond, carbon-carbon double bond. So controlling all that would seem to be a real challenge, and it is. But we've learned how to do it pretty well. One of the interesting features is that you can interconvert these two in the process, not these two, but all alkylidines of a syn and an anti-form just by doing the metathesis reaction, but they also interconvert in the absence of any olefin. So no metallocyclobutane intermediate. So they just rotate about this double bond. Now olefins don't do that readily. Some do, but very few. And the barriers to rotation about that double bond, so if you just rotate that 180 degrees, you get this one and vice versa. The barriers vary by 7 orders of magnitude, depending on what other things are on the metal. So that's a huge 7 orders of magnitude. In dollars, okay, $10 million. That's a lot of money. So it's a big deal here to have a rate of interconversion that varies from almost nothing to about 100 per second. So what do we use these for? We managed to control these reactions. It's taken a long time, but as I mentioned to somebody at lunch, maybe I'm a molecular engineer, right? I keep engineering these molecules, these catalysts, these initiators they are really for a catalytic reaction, engineering them so that we can get a given result. So what do you want to do? Well, one reaction that was very well studied when this reaction was first discovered was making polymers. So you can take a strained, we call it a strained carbon-carbon double bond, like in this fancy thing called a norbornadiene. This carbon-carbon double bond can be attacked. This one can't because it has 4 groups on it. And you can open that thing up, and then you can link them together. This unit, when you open it up, gets turned into a polymer, and you can write a mechanism for that. That'll be your homework for tonight. But you'd like to make it one structure. So when you make a polymer, of this general type, you can have a carbon-carbon cis double bond or a carbon-carbon trans double bond. And these rings can either point in one direction or the other direction or back and forth or just a mess. What you want is one structure. How do you make one structure? Nobody had ever made one structure before because they relied on something in a black box. And when you tried to make a polymer from this, you just got a mess. But this particular compound, through what's called an antiomorphic site control with this chiral ligand on the metal, will force this monomer to add to the same face of this metal carbon bond each time to give the first insertion product, and then that would react the same way, and that would react the same way, and you get this structure, all cis double bonds and all these rings pointing the same way. This has very important consequences in terms of properties, because when you have something that has a regular structure, it can crystallize. So it becomes very high melting, tough. If it's not a regular structure, then it's kind of a goo or a glue. So it's not as desirable. Maybe you want to make a glue, but usually you want to make something whose structure you can control. And that's been one of the big achievements in this area. But this is back in 1993, so we're more than 20 years on from that point. Back in '92, Bob Grubbs, this is the third recipient of the Nobel Prize, and Greg Fu was a postdoc with Bob and was at MIT for years, until a few years ago when he went back to Caltech, showed using one of the first molybdenum catalysts of this general type that you could do organic chemistry in a very quick, easy, beautiful manner. For example, you could take this compound with two double bonds here, you could just join those. When you join these two, you get what's called 2-butene, that's a gas. And when you join these, you get this 5-membered ring. You could make rings. Instead of opening them up, you could make them if they weren't too strained, and these are not too strained. So this compound, you can get ethylene out of that and make a carbon-carbon double bond there. That's a 7-membered ring, a 6-membered ring, another 5-membered ring, and so on. You could make rings. Now, nature likes rings because rings, in terms of, say, pharmaceuticals, if they are lying down on a cell surface, for example, they don't have a lot of degrees of freedom. They're not like a big floppy molecule. So there's more structure to an interaction involving a ring than a big floppy molecule. So rings are good. A lot of drugs are in fact rings. They don't have to be. There are many drugs that are not. Very simple compounds, and many that contain double bonds. Here's one that was made first by Amir Hoveyda in 1995. So the mid-90s was kind of a hot time for really doing something practical, but we weren't all the way by any means, as I'll show you. So he made something here that's called fluvorucin B1. There you see the ring, a lot of bells and whistles on it, but there was the double bond for that single bond before hydrogenation, and that was made by combining this species, or that carbon, and that carbon, that carbon, that carbon, and that carbon, and that carbon. And it was done efficiently. It was done in 92% yield, and it was done in 1995 by a catalyst that was, I think it was the molybdenum, so-called molybdenum F6 catalyst. That was one of the first generation catalysts. So metathesis is now used to make a lot of pharmaceuticals and drugs for many diseases. Hepatitis C is a cyclic peptide, osteoporosis, AIDS drugs, and other things. Not very many of them fully commercialized yet, but they will be very soon if they aren't now. Here are some of them. Here's recent papers of ours. These double bonds in red, if you can see them, are here, the important ones that are made by metathesis. And you see a lot of double bonds there, a lot of double bonds. So another thing is you can't attack every double bond or you just get a gigantic mess. So how you engineer this all so that the catalyst will only make that double bond. This is actually a mirror image through it. So there's a double bond there and one there that are formed. How do you do that with all these other double bonds around? It's incredible. So you have to engineer these reactions and make them very selective. So we're playing around with very tiny energy differences, and it's very difficult, but it's very important because it's such a clean and potentially useful reaction. Yazulactone, this is, many fragrances are simple cyclic esters or ketones that they put in perfumes. They smell nice, particularly this one called yazulactone. Okay, you can, this is called a ring opening, ring closing. That's a simple molecule. You add a catalyst with a chiral group on it, enantiomerically pure, and you can upgrade it to greater than 99% one chirality. That's that chirality, that one, that. It's this structure, period. 76% yield greater than 99% EE. So these are natural products that can be made easily from these precursors shown to the left, for example. So what was the big problem? Well, one of the big problems was actually taking these catalysts, controlling their reactions, but also I told you that olefins have isomers, right? There's a cis isomer and a trans isomer. And if you make both, then you're in trouble, because usually it's very difficult to separate the cis and trans isomers of olefins. And you can't crystallize one from the other, and sometimes if it's a big molecule, it's impossible. You can't do it. So you'd like to make one double bond selectively. And we figured out how to do that starting in about 2007. So if this is the type of intermediate, a ring in a molybdenum compound happens to be an imido aryloxide with this R prime here being a very large group. I'll show you what those are like in a minute. This is part of the second generation or third generation catalyst series with a pyrrolide on the metal. And you want to add a carbon-carbon double bond to this metal carbon double bond. If it adds, which it has to do to generate this product, all these R groups are going to be forced to point away from this gigantic group below this intermediate ring. And that's exactly what happens. So you get the cis alkene or Z alkene selectively. You make the new metal carbon double bond. It goes around again. I don't know if I have that here. Yeah, and makes the second equivalent and gets back to where you started. And so you can take this compound and the R1CH dimer or analog of this and do what's called a cross metathesis. So you make this cross product selectively. There are no other products, just the cross product. And it's Z. It's exactly what you want. It's the only product. So how we do that is really due to this realization that you've got to make rings where all the groups are forced on one side if you want to make these Z alkenes. I think I'm going to skip over this. Well, I can't skip over it. It's so beautiful. I can't skip over it. You notice that the third generation catalysts here have 4 different groups on them. So you have the alkylidine, the required alkylidine. They're all bulky groups. An imido group in this case, a big aryl oxide, and a pyrrolide. And that is one enantiomer of this ABCD compound. Of course, it's a mixture of 2. One, this one, and then the other possible one, where these 2 are switched or those 2 are switched, the other possible enantiomer. It turns out that in a metathesis reaction, and we showed this in a polymerization reaction, that the chirality at the metal, which starts out R, as I call it here, when it reacts with a cyclic olefin and opens up to start to make a polymer, it changes its chirality at the metal. Now, if the chirality at the metal, which is the only chirality present, dictates how that olefin comes in, and in fact, it comes in trans to this group, like that, makes that ring. Now, when you change the chirality, it comes in this way. So this one comes in that way, this one comes in this way, and that leads to a polymer with the opposite sort of configuration that I told you before. Instead of all the rings pointing one way and cis double bonds, you have cis double bonds with the rings first one way, then the other, one way and the other. And that's called syndiotactic. So now you can make polymers not only with one structure, but you can make both possible structures. And if you hydrogenate those, you can make plastics that don't melt until about 300 degrees centigrade. So there are no hydrocarbon polymers. I mean, things like polyethylene, polypropylene, they melt at 175 degrees, 135 degrees. On a very hot day in Abu Dhabi, that's not good. But 300 degrees centigrade, that's probably okay. So these are being commercialized now, made from very simple olefins like norbornene. I think I will skip over that one and just concentrate on the recent results in the last few minutes. Everything I've talked about, 99% of all of olefin metathesis, involves alkylidines or carbenes where R1 and R2 are usually H and some carbon group, right? RCH. Now you can make olefins of all sorts with other groups on them, carbon-carbon double bonds with other groups on those alkylidine carbons. And so can you make alkylidines that have groups X, where X is not carbon or hydrogen, like boron, nitrogen, oxygen, phosphorus, sulfur, silicon, or chlorides, fluorides, etc., on them, first of all, and will they do the metathesis reaction with other olefins in the way you would like it to work? So this is the Nature paper that we published about 2 weeks ago. I think I might have that on one of my slides. Dichloroethylene is made by adding chlorine to acetylene, which is a triple bond, and you can make both cis and trans forms, and it's dirt cheap because it's ancient, dirty 19th century chemistry. And it's about the last olefin you would expect to be attacked by a metal, which is what we call an electrophile at the metal, because this olefin is so electron poor. It doesn't have any electrons on it, so why should an electrophile, which wants electrons, attack it? But if you take this olefin, cis olefin, you can get it pure cis very easily. It's easy to separate from the trans, that's what happens. And then some cis olefin like cyclooctene, chop that, attach the two ends. You can make this product greater than 95% yield, and it's cis there and there. Unheard of. Nobody had ever done this type of reaction before. Now, these type of olefins are called alkenyl halides, and there's another Nobel Prize-winning reaction called a carbon-carbon single bond coupling that involves olefins, well, some of it, olefins with halides on the metal, on the carbon, on the olefinic carbon, just like we've done here. So this is exciting. You can make then reagents for other reactions, other clean catalytic reactions that cannot be made in any imaginable way using traditional organic chemistry. Bromofluoroethylene is available, widely available. I don't know how it's made. And we've shown that you can react it with this terminal olefin. This piece goes on there to give vinyl bromide, which you don't care about, and this piece goes on there to give this product as shown, cis. Now, fluorines on anything change the world pretty dramatically, and nobody has ever done a metathesis reaction with a fluorine on a double bond of the substrate involved. Maybe here that I point out that a significant percentage of drugs today contain fluorine in some form, and that's because it's not metabolizable. It's one of a kind. Fluorine just does things that other groups don't, and many drugs contain, of a certain type, sometimes like 50% of the drugs contain fluorine in some form. So they are very important in terms of pharmaceutical chemistry and drugs and the like. Here's the reference then to this Nature article, 459, the last issue of Nature this year. We were looking to see what was the catalyst, and again, it's through this collaboration with Amir Hoveda. What's the catalyst for this reaction? Well, you say this is the catalyst, right? Not necessarily, because it's what you start with. And it so happens that this reaction doesn't just take off. It sits there for a while and then takes off. And what that means is that whatever you start with gets turned into something else. So what is that? We really have to if you do a reaction of this type, you have to end up with a chloride CH on the metal as some intermediate. So we looked for that. And one of my postdocs spent a lot of time, and he found out in the case of the analogous dibromoethylene reaction that he could get in very low yield a compound in which this pyrrolide group had been replaced by bromide pyridine. So the bromide, he was hoping it was a CH bromide, but the bromide is on the metal. So, and the starting alkylidine was back formed again. So that set us to studying halo, halo derivatives of these ABCD catalysts. And it so happens that those are not very stable. We've never seen any CHCl intermediate, and even the halo versions are pretty unstable, and you have to have something else bound to the metal to stabilize them. As long as this comes off, then they will do the reaction. In fact, they're so reactive and so unique that they will do this cross-metathesis reaction on bis CF3 ethylene. There's fluorine again, and this is a refrigerant, very cheap, non-toxic, not poisonous. Well, I wouldn't drink a gallon of it, but it's relatively safe. So chop that, and you get these two products. This is cooking oil, okay, an oleic acid ester. And nature makes it selectively cis. We have that selectively cis, and our products are selectively cis, greater than 98%. And the yields are also good, unheard of, never been done before. And we're very, very excited about that. Here's another version of this cross-metathesis. So put that with that, put this with the other end. You don't care about one of them. This is the product you care about, and it's all cis, greater than 97% shown here. So all this led to a Nobel Prize, as you've heard, and this is what it looks like. On December 10th, the day that Nobel died in 1896, and the Swedish Academy spent about 5 years and the first doing what he wanted, and that is to set up a foundation to give out prizes. The first one was in 1901, and this one was in 2005. So this is what it looks like in the Symphony Hall where the Nobel ceremonies are held. That's the big N. And some of you probably can't see that young lady there. That's my wife. And on each side of him are my two sons, or her are my two sons. Here are all the people who are going to receive a Nobel Prize. Here are the other Nobel laureates just in town who want to get dressed up and sit on the stage. And this is the Swedish Academy, and this is the royal family. And then you are asked to stand up. This guy's still trying to figure out what we did. And you're supposed to go out and receive the prize from the king, each of us. And it sounds simple, but people sometimes can't do it. You've got to back away, and you've got to bow to him, and then you've got to turn around, and you've got to bow to the academy back there, and then you've got to turn around and bow to the audience, like that. Then you got to go sit down. So this is my lovely wife, Nancy, who's in the front row. That's me, obviously. There's Eric and Annabelle, who they weren't married at the time, but now, and have two grandchildren, both boys. This is Andrew and Rebecca, and they have a grandchild, Nora, who's going to be 7 years old on the 18th, which is, I think, 3 days from now of April. So after that, it was all, dancing and eating and drinking and so on, a lot of celebration. So beautiful people, everybody looks, all the guys are handsome, women are beautiful, and it was a wonderful time, wonderful time. So I can't do any of this, or didn't do any of this, without support, and thank you, because you paid taxes. The National Science Foundation, NIH, and the Department of Energy for each of these subjects, and Amir Hoveda is really the one that I've been compatible with and found a way to translate what I learned as an organometallic chemist into something that's useful for organic chemistry, and he's now coming back with discoveries too. So we go back and forth, and as I said, we were just renewed for, I think I said that, for 4 years by the NIH, and that's our 18th year of collaboration. And this is my group now. They're all postdocs. I graduated my last graduate student in 2015, my 83rd student. a prime number. She was a good student. And so the only American here is this fellow. He's from Trinidad, Chinese, Japanese, 3 other Canadians, Russian, Korean, and Sri Lankan, my only Sri Lankan I've ever had, or probably ever will have as a postdoc or graduate student. So they are beavering away at home, and so I'm eager to get back and see what's happened. I want to just close with thanking you all again for the invitation, and hope you enjoyed the talk. Thank you. If it's not too late, yeah, I'd be happy to take questions.
Is there a question? Is this on? All right, I want to.
Oh, here's a question.
Professor Schrock, that was an excellent talk. Just to let you know, some of the work that you did, we used to have to study for our cumulative exams. So,
There's some good cum questions here, yeah.
without a doubt. So, my question is, I'm a polymer chemist by training, so I work with Frank Harris at the University of Akron. And so, with that being said, Professor Prof would mention things about being non-tactic. So, I love your analogy with the syndiotactic and the isotactic polymers. And I noticed that you did that with 2 generations of catalysts. Is that correct? Did I read that on
2 different generations, because in one case, the monomer has to approach one side of the double bond. That's the enantioselective or an enantiomorphic site control. And in the other case that I didn't go into, well, I guess I did in the end, it approaches one side and then the other, and one side, then the other. And it's amazing, and it's because of the chirality at the metal that switches each time. But never been done before in polymer chemistry that I know of.
That was excellent work. Can you tell me about the percentage of catalysts that you had to use in both cases? Because I guess
Yeah, this is a good question. And that doesn't mean I don't know the answer. I do know the answer. Usually we use when we do catalysts or do make polymers, maybe 2%, but you can go down as low as you want. The problem is if you start to make really high molecular weight stuff, then you have difficulty in handling it. And it's better to keep the molecular weight down if you're just doing sort of organometallic chemistry. I call baby polymer chemistry, like I do. Keep the molecular weight down. So we usually use 2%, maybe 1%.
Okay, is this on? Is this on? Yes, okay, don't leave. So we typically end the Sweeny lecture with an award. So each year we confer an award, the Sweeny Achievement Award, to the best undergraduate who's graduating in June. Now, this student is someone who has earned exceptional grades in their classes, but has also been a member of the department as a research student, usually for 2, sometimes even more years. This year, also for the first time, we're going to confer something we call the Student Citizen Award. This is a student who has participated in the life of the department, helped the department in many ways, including help, we're in trouble, we need you right now. And so this year, we're going to be conferring the Sweeny Achievement Award and the Citizen Award to the same student. So I'm going to ask Ms. Ben Nguyen to come up here to receive the Sweeny Award. No, just the 2 of them. No. All right, thank you. All right, I would like to end with one more thing. I'd like to thank the people who actually put this together. And I'll start with, I think there's 3 people, there might be more. Saraswati in our department and as a CLT, and Sharif El-Hakim. They really make the whole thing come together. But also our one and only Andre Gitiano makes the whole thing work. Anybody else?